Okay, going strong. Question 6. Calculate the molarity of a solution prepared by dissolving 11.85 grams of solid KMnO4 potassium permanganate in enough water to make 750 milliliters of solution. So before we begin this problem, you need to remember, recall, think back to the good old days of first year chem where life was easy. Molarity is equal to moles per liter. So if we're going to solve for the molarity of this solution, we need to know how many moles and in what volume in liters we have that number of moles. We're given a mass in grams and we're given a volume in milliliters. I can slip in the volume in milliliters here pretty easily, making sure to convert it to liters in my head to 0.750 liters. To get the number of moles from the mass in grams, we're going to take the 11.85 grams of potassium permanganate and use our amazing dimensional analysis skills, MnO4, to convert to moles. Again, 1 mole, where do I get this number from? The periodic table. We're going to need 1 potassium, 1 manganese, and 4 of those oxygens to give us a value of 158.04 grams. Quick conversion here will tell me that, wait, before we solve, let's just do this in our minds. Let's estimate, do we have 1 mole? Well, if 1 mole is 158 grams and we only got 11.85 grams, we definitely have less than 1 mole. We have less than a tenth of a mole, because a tenth of a mole would be like 15 grams, 16 grams. So we are looking at a number that's definitely less than a tenth of a mole. So when we do this in our calculator, we end up with 0.07498 moles. We're feeling pretty good because it matches our estimation of less than a tenth of a mole. Now, this is not our final answer. We need to take this number and bring it down here to our molarity calculator, 0.0498 moles. And when we solve for molarity, we end up with 0.09997 molar KMnO4. And if we use sig fig rules, we only need 3. The volume is going to limit our number of significant digits, which will give us 0.100 molar KMnO4. Boom. Next question. Question number 7. Says, calculate the mass of sodium chloride needed to prepare 170 milliliters of a 0.500 molar sodium chloride solution. So again, another problem that works with the magical molarity formula, which is moles per liter of solution. As we work to solve this, we're given the molarity this time, which is 0.500 molar. We're looking for the number of moles, X. We know the volume in milliliters. Again, I'm going to do an amazing calculation in my head to get that to 1.750 or 0.175 liters of solution. If we solve for X, we're going to do a quick multiplication here to get X by itself. X equals 0.875 moles of NaCl. Again, a lot of work already, haven't solved the problem. In order to solve this, we need to then take our number of moles and convert it to grams. So we're going to take our 0.0875 moles of NaCl, do some dimensional analysis, moles, NaCl, grams, NaCl. Again, this number is going to come from the periodic table of the elements. We're going to take 1 sodium and 1 chlorine, add them together, and we end up with 58.44 grams. Whoa. 0 point. So when we solve this, we end up with 5.11 grams of sodium chloride that's dissolved in that 175 milliliters. Boom. Okay, next questions. Taking it up a notch. We need to, in this problem, answer two questions. First, it says determine the molarity of the iron 3 ions and sulfate ions in a solution prepared by dissolving 48.05 grams of iron 3 sulfate in enough water to make 800 milliliters of solution. Again, a problem that's going to require our knowledge of the formula for molarity, which I'm just going to slam up here for our reference. Molarity is equal to moles per liter of solution. To solve this, I'm going to start with my 48.05 grams of Fe2. Fe2 SO4 3 iron 3 sulfate, and we're going to convert that first to moles. Again, grams, and I'm going to be very careful about my labeling here, so you can sort of see how we get from one place to the next. Super tedious, I know, but really, really important. Not so much on the multiple choice, but definitely on the free response section of your exam. So just, be very careful about labeling when you're on that free response. It will very much help the graders understand your thought process and where those numbers are coming from. Don't leave unit list numbers in your dimensional analysis. Okay. This mass in grams, again, we can find the molar mass from the periodic table. Wow. This one's a doozy. We've got Fe2SO4 3. So we're going to need to do iron twice. And then we've got 3 sulfurs, 1, 2, 3, and then we've got 12 of 12 oxygens. So we're going to add all those together, and when we do that, we get a mass in grams, a molar mass of 399.9 grams. We're looking for the molarity of just the iron 3 ions, though. So our next step is to go from moles of iron 2 sulfate to moles of iron 3 ion. And to figure out this relationship, you just have to look at the formula for iron 3 sulfate. For every one of these, there are 2 iron 3 ions. So 2 for every one of these. And when we solve this, using my incredible mathematical skills, so we get 0.24403 moles of the iron 3 ion. Woo! That unfortunately does not answer our question. We're asked to solve for the molarity, not for the number of moles. So we're going to shrink this down a little bit. And then we're going to plug the number of moles, 0.2403 moles, in 0.800 liters. Again, careful, watch out what I did there. I converted milliliters to liters to get concentration of 0.300 molar for the Fe3 plus ion. Boom. And there's our answer to question number 8. Now, some of you mathematical geniuses will be able to simply recognize that based on the relationship in the formula, the concentration of the sulfate ion is going to be 1.5 times larger than the concentration of the iron 3 ion, simply because in the formula, the ratio of sulfate ions to iron ions is 3:2, or 1.5 times as much as the iron ion. And if you can recognize that, awesome. I'm going to work through as quickly as possible the dimensional analysis required to do it for the sulfate ion. But again, some of you probably recognized already how you could figure that out without doing all this mumbo jumbo that I'm about to do. 48.05 grams of the iron 3 sulfate. It's going to start exactly the same as the last one. Whoops. Again, we're going to convert first to moles. And, as you look at these problems all the time, we're converting to moles first. Moles. Even if we're not looking for moles, it's the first thing we do. 399.9 grams Fe2 SO443. Awesome. Now, here's where the change is going to come. We're going from moles of the iron iron 3 sulfate, this time though to moles of the sulfate ion. So for every one of these, there's 3 sulfate ions. Or for every 1 mole, there's 3 moles of sulfate ions. So you can, I think, begin to see here sort of how we're going to end up. Our number of moles are going to be, of sulfate ions, are going to be greater than the number of moles of iron 3 ions in the same volumes. We get 0.3605 moles of sulfate. I'm going to shrink this down. Baby, are you down? Okay, and then we're going to, again, solve for the concentration by taking that number of moles in the 0.800 liters, which will give us 0.0 molar sulfate ion concentration. Boom. And again, many of you math geniuses can probably recognize that 0.450 is 1.5 times larger than 0.300. And again, you wouldn't have to do all this jazz to figure out the ion or the molarity of the sulfate ion simply by looking at the relationship of iron 3 ions and sulfate ions in the original formula. That was the trickiest one of the day. So moving on.